This paper, Causal Machine Learning, a Survey and Open Problems, delves into the growing field of causal ML, which aims to incorporate causal knowledge into machine learning models. What are the key challenges that traditional machine learning methods face, and how does causal ML address them?
Traditional machine learning methods excel at finding associations in data, but they often struggle when deployed in real-world settings where the data distribution shifts. This can lead to poor generalization performance, biased predictions, and a lack of interpretability. Causal ML addresses these issues by formalizing the data generation process as a structural causal model, SCM, which allows us to reason about the effects of interventions and counterfactuals.
Can you elaborate on the concept of a structural causal model, SCM?
NCTML represents the causal relationships between variables in a system using deterministic functional equations. It allows us to model how changes to the system, called interventions, affect the observed data. For example, we can use an SMIMO to estimate the effect of a new drug on a patient's health outcome, taking into account other factors that might influence the outcome.
That's interesting. How does causal ML leverage SCMs to address the challenges of traditional machine learning?
Causal ML uses SEMs to learn models that are more robust to distribution shifts, less prone to bias, and more interpretable. For example, in supervised learning, causal ML methods can identify invariant features that are predictive of the target variable across different environments. This helps to eliminate spurious correlations that can lead to poor generalization.
Can you give a specific example of how causal ML can improve supervised learning?
Imagine a data set of images of cows, where most of the images are taken in alpine pastures. A traditional supervised learning model might learn a spurious association between grass backgrounds and the cow label. This could lead to poor performance when the model is tested on images of cows in different environments, such as beaches. Causal ML methods can identify the invariant features that are truly predictive of the cow label, such as the cow's shape and texture, and learn a model that is invariant to the background.
So causal ML can help us build more robust and reliable models. What about the issue of interpretability?
Causal ML can also improve interpretability by providing explanations that are grounded in causal relationships. For example, we can use causal attribution methods to identify which features are most responsible for a model's prediction. This can help us understand why a model made a particular decision and identify potential biases.
That's very helpful. Can you give an example of how causal ML can be used to explain model predictions?
Imagine a loan prediction model that rejects a loan application. A causal explanation method could identify the most important features that contributed to the rejection, such as the applicant's income or credit score. This can help the applicant understand why their application was rejected and what they can do to improve their chances of getting approved in the future.
It seems like causal ML offers a powerful framework for addressing many of the challenges of traditional machine learning. What are some of the key areas where causal ML is being applied?
Causal ML is being applied in a wide range of areas, including supervised learning, generative modeling, reinforcement learning, and fairness. In supervised learning, causal ML methods are being used to improve the robustness and interpretability of models. In generative modeling, causal ML methods are being used to create models that can generate samples with specific attributes or edit existing samples in a controlled manner. In reinforcement learning, causal ML methods are being used to improve the efficiency and robustness of learning algorithms. And in fairness, causal ML methods are being used to develop models that are less likely to discriminate against certain groups.
That's a broad range of applications. What are some of the limitations of causal ML?
One of the biggest challenges in causal ML is the difficulty of obtaining ground truth data for training and evaluating causal models. Real-world interventions are often expensive, unethical, or time-consuming to collect. This means that researchers often have to rely on simulated data, which can be manipulated and may not generalize well to real-world settings.
So the lack of real-world data is a significant hurdle. Are there any other limitations?
Another limitation is that causal ML often relies on strong assumptions about the data generating process. These assumptions can be difficult to verify and may not always hold in real-world settings. If these assumptions are violated, the results of causal ML methods can be biased.
That's a crucial point. How can we address these limitations?
One way to address the limitations of causal ML is to develop more robust methods that are less sensitive to violations of assumptions. Another approach is to develop more sophisticated methods for identifying and mitigating confounding variables. Finally, we need to develop more realistic and reliable benchmarks for evaluating causal ML methods.
It seems like there's still a lot of work to be done in causal ML. What are some of the most promising areas for future research?
Some of the most promising areas for future research in causal ML include developing more efficient and scalable algorithms for learning SCMs, exploring the use of causal ML for tasks such as adversarial robustness and meta-learning, and developing new benchmarks for evaluating causal ML methods.
It's exciting to see the progress that's being made in causal ML. What are your thoughts on the future of this field?
I believe that causal ML has the potential to revolutionize machine learning by enabling us to build more robust, reliable, and interpretable models. As the field continues to develop, we can expect to see causal ML methods being applied to an even wider range of applications, leading to significant advances in areas such as healthcare, finance, and robotics.
Thank you for sharing your insights on this fascinating and rapidly evolving field. It's clear that causal ML has the potential to make a significant impact on the future of machine learning.